First example. Find the exact area under f of x equals x to the third plus 3x plus 4 between 0 and 2. Okay, so we have to talk about the following first. Here's the interval. Here is 0, here is 2. I divide this interval, 2 minus 0, divided by n. So n subintervals. And n will go to infinity in the limit in a minute. So this first subinterval has the width 2 over n. The next subinterval has the width 2 over n. The next subinterval 2 over n. The ith interval has the width 2 over n. The I plus first subinterval has width 2 over n. Then I get here, this is n minus 1 has 2 over n, and this is the nth interval which has the width 2 over n. Now this first point is x1, which is 0 in this case, plus 2 over n. The next point, can anyone dictate the second point? Is x2, which is 0 plus 2 pieces. 2 times 2 over n. Can anyone give us the third one? x3 is 0 plus 3 of 2 over n. Of course, what I'm getting at is here. This is what I need. I need the xi, which is 0 plus how many 2 over n's? Of course. That's all I need. Okay. So there are a lot of preparations before we determine that area. First preparation is delta x. Delta x, I'll say preps. Delta x, 2 minus 0 over n. 2 over n. Step number 2, can anyone give us xi? So 0 plus 2i over n, which is 2i over n. Preparation number 3. F of xi. No, we're not there yet. F of xi. Can anyone dictate? This is our xi, and it has to be plugged in here. 8i to the third over n to the third plus times 2i, 6i over n plus 4. Okay, finally, area equals limit as n approaches infinity from the sum from I equals 1 through n, from delta x, which is 2 over n, multiplied by f of xi, which is 8i cubed over n cubed plus 6i over n plus 4. This would go in front, as we said, because it's a factor. It does not depend on I. If it depended on I had to multiply it. But it does not depend on I. It's a constant. So limit as n approaches infinity from 2 over n. And if you remember, we said that the summation notation has a property, that the sum of ai plus bi plus ci is the sum of ai plus the sum of bi plus the sum of ci. So I'm going to use that property right now. So the sum from I equals 1 through n, from 8i to the third over n to the third, plus the sum from 6i over n, from I equals 1 through n, plus the sum of 4 from I equals 1 through n. Now, I realize that this is a constant, does not depend on I, multiplies I to the third, has to go in front, like with that. I realize that this is a constant, it has to go in front. And this is a constant multiplied by 1, and it has to go in front. So I will rewrite limit as n approaches infinity 2 over n, 8 over n cubed, the sum of I cubed, plus 6 over n, the sum of I, plus 4 sum of 1. Notice that I dropped the I because just for simplicity, I'm going to come back to that. Let me write it. I don't want to confuse you. But I just discussed this, and I even proved one of them. So I know what this equals to, I know what this equals to, and I know what this equals to because I'm going to replace them in a minute. What does this equal to? What does this equal to? And what does this equal to? So at this moment in time, I remove these three, they're gone, and they are replaced with algebraic expressions. Stay with me, it's not done. And I lost track of where I was. That's 12, that's 13. And that's 14. Ready? Limit. As n approaches infinity, 2 over n stays outside. So I have 8 over n cubed multiplied by n squared, and I'm going to square that, n squared plus 2n plus 1 divided by 4. This is just the first term here, plus 6 over n, and I just write n plus 1 over 2, plus 4n. I like it because 2 of those are going away. This is going away. This is going away. I will not simplify n with n because there is an n in the denominator. So I will have to multiply if I simplify. So I'll leave it alone. I realize that have 2 over n and the least common denominator is n. The top with the 2. 2n squared plus 4n plus 2. n in the denominator, that just distribute here, plus 3n squared plus 3n. And of course, this one needs to be multiplied by n. So finally, plus 4n squared. Almost last step, limit as n approaches infinity, n squared. 2 plus 3 is 5, 5 plus 4 is 9, 9 times 2 is 18. 4 plus 3 is 7 times 2 is 14, and 2 times 2 is 4. When I apply infinity, I have infinity over infinity, but I know a rule that will save me anytime I have infinity over infinity, and that is good. So I have 36n plus 14 divided by 2n. Again, infinity over infinity. So I get the answer to be, yes, it took us 20 minutes to do this, but this is the exact area. Nothing left over.
So on the test, would you like ask us to do either or specifically one?
I will ask you to show the approximation with 4, not more than 4.
Okay.
I can't do it. I didn't even do myself the 8 because you got the pattern. That's all I care about. And you will be asked to do one of this. We are limited here. As you've noticed, we don't have any summation for sine, cosine, tangent, cotangent, any other function, but polynomial functions, degree 1, 2, and 3, that's it. We cannot do the limit of the Riemann sum for anything else. Just polynomials, degree 1, 2, or 3. There's nothing else. We are not equipped to do that or use Riemann sum, the limit of the Riemann sum to determine the area. Okay.
Nobody's figured out what item 4 is?
No. It's not that we didn't figure it out, but it's that's all we need. So if you open your book, you will see those 4 formulas. They must be here. Let me see where they are. Oh yes, they are on page 375. Here they are. They give you some properties, and the bottom of page 374, they are giving you 3 of those. And the first one has to be somewhere else. Somewhere, it's here. Any questions? Any questions? Of course, the function has to be a continuous function, because otherwise we get into other situations. Any questions? I suggest we do an approximation and also another limit of the Riemann sum. Is that okay? Okay, so let's choose a function. Oh, and let's use 4 subintervals.
Subintervals. Actually,
You can make up a function.
yeah, let's just do the area from 0 to pi of sine. If we're breaking in.
Yes, we can. We can do that with the approximations. Yes, from 0 to pi
Yes.
of sine. Okay. And how many subintervals?
4.
You want to use 4? Okay. With 4. So first of all, we have to graph the function. So 0, pi over 2, pi. At 0, the function is 0. At pi over 2 is 1. So this is the graph. And we want to divide it in 4. Would you like to do the midpoint? Would you like to do the leftmost point? I think we should do maybe 2 of those. You choose, the midpoint and one other. Okay, so we want to determine the area using left with 4. We want to use the area, find the approximation with midpoint 4. We cannot do this exact with the limit of the Riemann sum. As I said, it has to be a polynomial function, degree 1, 2, or 3. Very good. So the leftmost point. Here is the area, first area with the leftmost point, height of 0. This is the area with the leftmost point for the second one. And here's the area with the leftmost point. Oops, for the third one. And here is the leftmost point. So then the area left for will be approximately. In order to determine the width of the interval, I have to write, this is, remember the interval is a comma b. So I have to write that delta x is b minus a over 4, which is pi, so delta x is pi minus 0 over 4, so it's pi over 4. So then pi over 4, and in parentheses, f of 0 plus f of pi over 4 plus f of pi over 2 plus f of 3 pi over 2. It's pi over 2 plus 3 pi over 4. So pi over 4, and in parentheses 0, plus f of pi over 4, I know it's the square root of 2 over 2. F of pi over 2, I know is 1. And f of the 3 pi over 4 is the square root of 2 over 2. So I have pi over 4 multiplied by 1 plus the square root of 2. And then I can put that in the calculator and I'll tell you what it is. So pi multiplied by 1 plus the square root of 2 and divide everything by 4. I got 1.896. So approximately 1.8961. Now for the midpoint, I will have to use the calculator more because the midpoint, so the function now will look like this. I mean, still the same graph, of course. So but now this is the height. This is the height. This is the height. And this is the height. So this was pi over 4, this was pi over 2, this was, here's pi. So 3 pi over 4. So therefore, now this is pi over 8. Now this is 3 pi over 8. Now this, so I have 1, 2, 3, 4, 5. 5 pi over 8, 6, 7. And 7 pi over 8. So now the area with the midpoint 4 is approximately still the same base, but it's f of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8 plus f of 7 pi over 8. So again, I'm going to create a list. Here's how I'll do it. Okay, second quit. Go back to list. I'm going to edit again. So now I have pi divided by 8. 3, 5, and 7. 3 pi divided by 8. 5 pi divided by 8. 7 pi divided by 8. Now on the other side, I highlight the top and I put in sine. Don't let me forget to multiply by pi over 4. Because I get that sum and then I have to multiply by pi over 4. So this is sine of L1. And the mode has to be in radians. I'm checking the mode. Good. So second and list, no. Okay, so now I want to do the previous stats on L2, and the sum is 26131, but I have to multiply this number by pi and divide by 4. So 2 point, oh, I didn't write it down. So 2.6131. Okay, I got it. 2.3161 multiplied by pi and divided by 4. $29.10.
So 29.
Yeah, how's the first one off by so much?
Yeah, I was just looking at it. So between, this is 0 and pi over 2, and this is pi over 2, and this is 3 pi over 2, and this is pi. What did I do on the previous one? Let me check. So I had pi over 4, yes, pi over 4 times leftmost point, and pi over 4 times, so this is pi over 4, and this is 3 pi over 4. So 0 times pi over 4 plus pi over 4 times f of pi over 4 plus pi over 4 times f of pi over 2. And this is the square root of 2 over 2, because we are looking at sine. This is indeed 1, this is square root of 2 over 2, and this is 0. So I had the square root of 2, yes, 2 to the square root of 2 is the square root of 2 plus 1 times pi over 4. And this calculation is correct? Did anyone check?
I get the same thing.
Okay, so pi plus 1 square root of 2 divided by 4. Okay. Okay. So here, still base times height. And it's right in the middle, right? Pi over 4 divided by 2 is pi over 8. And then 1, 2, 3, right? This is 3 pi over 8. Are my numbers correct? This is 5 pi over 8, and this is 7 pi over 8.
Something in the calculator didn't do right.
Let's take a look. So, one more time, the mode is in radian. Okay. So, let me look at my list again.
Oh,
You didn't divide by 4.
you did just pi 4.
I didn't divide.
Yeah.
I multiplied.
Right.
Oh.
There we go.
Okay. Sorry about that. 1.819. Okay, ready? For something much easier than this. Oh, we wanted to do one more Riemann sum. Okay, So we looked at an approximation, and now let's look at the Riemann sum. Please give me any function you want, linear, quadratic, or cubic. And let's make it a little bit more difficult. I'm going to use, if I use 0 as the leftmost point, it's always easier. So I'm going to say 1, 2 this time.
So 3x squared plus 4 or minus 4x, whatever.
Good enough. It's quadratic. Perfect. I need 3 preps. What is the first prep? Perfect. What is delta x equals to? What does it equal to?
Should be, well, n or
The formula is b minus a over n,
it's
where this is a comma b. Very good. So 2 minus 1 over n. So delta x is 1 over n. Good. Prep number 2. Very good. The leftmost point, or value, which is 1 now, not 0, plus how many delta x's? I delta x's. So 1 over n times I will be 1 plus I over n. Prep number 3. What do I have to find? F of xi. Very good. F of xi is 3 in parentheses, what? 1 plus I over n, plus 4 in parentheses, 1 plus I over n, and plus 1. Good. I have to square this. First term squared plus 2 times the first times the second plus the second term squared plus 4 plus 4i over n plus 4. You see why I cannot put this in the sum? I have to thank you. I have to simplify it as much as possible first. Otherwise, there's going to be a mess in the sum. So then 3 plus 6i over n plus 3i squared over n squared plus 5 plus 4i over n. In descending order, 3i squared over n squared plus 10i over n plus 8. Now it is fully simplified. Now I can put it in the limit of the Riemann sum. So now I know that the area is exactly the limit as n approaches infinity. I would like to put the delta x in front so I don't have to write it again. And times the sum of this. 3i squared over n squared plus 10i over n plus 8 from I equals 1 through n. It's a lot of writing in this limit of the Riemann sum. Now please tell me what will be the next step. What should I do next?
Pulling out the constant.
Yes. Perfect. So then limit as n approaches infinity from 1 over n, 3 over n squared, the sum of I squared, plus 10 over n, the sum of I, plus 8, sum of 1. But I know, yes.
And now we plug in for the I squared.
Exactly. Now I have to replace this, I have to replace this, and I have to replace this. And from this point on is only algebra. What is this equal to? What does this equal to? Good. What does this equal to? It's n plus 1 divided by 2. But this is the ugly one.
That is the ugly one.
Yes. So it's n plus 1. The same thing with this, but there is a 2n plus 1, and there is 6 in the denominator. It's the one that we proved today. So maybe it was a good idea to pick that one, because now at least you saw it, how it's proved. Okay. So then, limit as n approaches infinity 1 over n, 3 over n squared times n plus 1, 2n plus 1 divided by 6 plus 10 over n times n plus 1 over 2 plus 8n. Your book shows a different thing. They separate the terms. That's fine. That's fine too. I prefer this because I think we should be able to do this by now. Okay, so let's see what will be the least common denominator. If I simplify the 3 with 6, then I have 2 in the denominator, and there is a 2 in the denominator, and I'm not going to simplify it here. That's good. I'm going to simplify an n with an n. So the least common denominator is 2n, the least common denominator is 2n, this one needs a 2n. So limit as n approaches infinity 1 over n. Let's see what we have. So 2n, all I have to do is just multiply these two. There is nothing else left. There is 2n in the denominator, this is 1. So 2n squared plus 3n, very good, n plus 1. Excellent. There is the 2n in the denominator. All I have to do is say plus 10n squared plus 10n. And finally plus 16n squared. Very good. It's a good pick. It wasn't really difficult. Okay, so then limit n approaches infinity. Now the denominator is 2n squared. I have to multiply. 16 plus 10, 26, 28. 3n plus 10n, 13n, and plus 1. Again, I apply L'Hopital's rule twice, and the answer would be? Very good. It's from what we know. Same degree over same degree. The horizontal asymptote is 28 divided by 2, which is 14.
Are there problems like this in the book?
They show an example here, but they show this example already when they get to the definite integrals. So I don't want to do that. I want to show the example first and then look at definite integral.
So when practicing, where could be a practice problem?
For this particular, which is what we do in class. I can't find another example than the one that I showed you.
There's like suggested exercises that we notice. Do you think are those supposed to do?
Just create any function.
Okay.
This is what I would do. Create any function at any interval, and then I'll show you how to find the exact area in a blink. And then you will be able to check yourselves. Or you bring it to class and say, hey, did I do this correctly? Okay. Right. I'll stop in about 10-15 minutes.
So
Yes.
we use this for ratios?
We use, you mean the limit of the Riemann sum?
Right.
We use it to determine areas on the graphs.
Right, so, but if we were to have a function that's like polynomial divided by polynomial.
Oh, we cannot do the limits of the Riemann sum for ratios. No,
We can't, okay.
no. We don't have any tools.
Okay. I'm just trying to figure out what's gonna be on the test, like what can be on the test. 'Cause that sounds like it'd be a nightmare.
Okay, so you will have an approximation, not more than 4 subintervals, definitely, and you will have a polynomial, degree 1, 2, or 3, Either,
to do
either
limits.
2 or 3 to do this. And you will be able to check it in a minute. I'll show you how to check it. We'll go back to the functions that we had in a minute, and we'll check the area. Okay? Good. Now, the fundamental theorem of calculus has 2 parts. I would like to show just one of the 2 parts tonight so we can check our integral. So we can check our areas. Okay? So, the fundamental theorem of calculus has 2 parts. I'm only interested in one right now, and we'll discuss the other one next time. Okay. There exist 2 types, before we talk about that, 2 types of integrals. One is definite, and the other one indefinite. First difference between the 2, a definite integral is always a number. Result, a number. Here the result is a function. So before we talk about the fundamental theorem of calculus, the part that I need for tonight, we have to mention the fact that there exist 2 types of integrals. One definite and one indefinite. The question is, and I'd like to talk about the definite integral. The question is, what does this mean? What is even the word integral? What does it mean? Correct. So it's an area. It's a sum. It's a sum. Or it's a sum. A long S. So all these kind of mean the same thing. So now the definite integral has the following notation. The integral from a to b, which will be the area, from what? So this is the sum. What was the sum from? Base times height. What did we denote the base by?
Base delta x.
Good. And the integral will be denoted by dx. And what was the height? F of x. And this is the exact same thing with the limit as n approaches infinity from the sum from I equals 1 through n from delta x f of xi. The definite integral and the limit of the Riemann sum will always give the same thing. This we have seen. It took us 2 pages for each problem, right? Now this is much easier, but I have to explain using the fundamental theorem of calculus how to determine this. This we know, very limited, only for polynomial functions degree 1, 2, or 3. But how do we determine this? And we learn that from the fundamental theorem of calculus. And here is what we need to remember. The integral from a to b from f of x dx is, can anyone remind us what is the antiderivative of f of x denoted by, and this is what I started with the first moment tonight. Right. F of x evaluated at, which really means f of b minus f of a. This is the way we calculate definite integrals. the integral from a to b, from f of x dx, is the antiderivative evaluated at a and b, but subtracted from the numerator, from the upper limit, subtract the lower limit. So we had a few minutes ago, like, where was it? Okay, we chose a function that was, you gave it to me, we made it up, 3x squared plus 4x plus 1, and we got that the area was 14, wasn't it? Correct. We want to check that the area is indeed 14. So in order to find the area, I will write the integral from, we used 1 to 2, correct? So the integral from what to what? 1 to 2, from f of x, 3x squared plus 4x plus 1 times the base, which is dx. Okay, so I have to find the antiderivative of 3x squared
X cubed.
over 3. 3x cubed over 3 plus 4x squared over 2 plus x evaluated from 1 to 2. Let's do this one more time.
So we don't put a plus c.
Very good question. Very good question. This should have been f of x plus c, where when I plug in b and then I subtract when I plug in a, the c will go away.
Okay.
Let me write it because you may have not.
No, that's true.
Is it clear?
Yeah.
Okay, perfect. So one more time. 3x squared, the antiderivative of 3x squared is 3x cubed over 3. I'm going to simplify in a minute. Plus 4, the antiderivative of x is x squared over 2. The antiderivative of 1 is x. Agreed? Good. So I will simplify. So then I have x cubed plus 2x squared plus, you couldn't have chosen a nicer function. Thank you. No denominators, no nothing. Good. So now I plug in 2 and I get 8 plus 8 plus 2 minus when I plug in 1. 1 plus 2 plus 1. 16 plus 2, 18 minus 4.
That's a lot easier.
We can't. We have to do the limit of the Riemann sum because we need to understand how those areas are created. And then we can put this in. And we had another one. What was it? Sine between 0 and pi? 0 and pi, yes. Okay, very good. Let's determine that too. So we want to find that we did not find exactly. We couldn't because we don't have the limit of the Riemann sum of that. But now the area is the limit from 0 to pi from sine x dx. What function prime is sine x? Very good. Negative cosine x from 0 to pi. Negative. Leave it outside. Cosine pi minus cosine 0. Cosine pi is negative 1. It's on the, yes, negative 1. Cosine 0 is 1. So negative 1 minus 1, negative 2 with minus in front.
And it was really close to 2. It was a little bit below and a little bit above when we did that.
Very good. And I think we chosen one more function at the beginning. What was that? I forgot. What was the first function we chose? So we can check that as well. Of course, we did not determine. Oh, yeah, no.
We did Riemann's.
Riemann sum on x cubed plus 3x plus 4. So the function is f of x, x cubed plus 3x plus 4. The interval was 0, 2. And our answer was, 5 pages later, 18. Okay, so we got 18 before. So therefore, the area is the integral from 0 to 2 from x cubed plus 3x plus 4 dx, which is antiderivative of x cubed plus 3 x squared over 2 plus 4x from 0 to 2. Here's why I like 0 to 2, because when I plug in 0, I get 0. So I don't have to subtract anything. So the only thing that I have to do is just plug in 2. So this is 16 over 4, which is 4. 4 over 2, which is 2, times 3 is 6. 4 times 2 is 8, and voila.
It's so much easier.
Thank you. Any questions? Now let me tell you what we accomplished tonight. I'll stop there.